All right, everyone. Welcome back to Robo Papers. Today, we're super glad to have Gao Yang from Tsinghua University going through with us his paper FP3, a 3D foundational policy for robotic manipulation. So,
Yeah,
very happy to have you, Gao Yang.
yeah, very nice to meet you again.
Yeah, it's good to see you again. Yeah, so maybe just a quick one for the audience. Like, could you give a quick intro about yourself, like how you get into this space? What's
Yeah,
your journey
sure.
like?
So I'm currently a assistant professor at Tsinghua University. I'm mostly doing robotic research, and previously I was a PhD student at UC Berkeley. My advisor was Trevor Darrow, and he is into the computer vision space. Yeah, so I started in pure computer vision space, but later I find it quite interesting to combine vision technology with the capability to move. So yeah, back into the Berkeley time, I also work with Professor Sergey Levin and Professor Peter Bill, and they are pretty much into the robotic space. And later I find it really interesting to work on how to make robot move. Yeah, that's how I made there. And so besides the Tsinghua professorship, I'm now also founding a startup called Spirit.ai, which
Awesome.
is a general purpose robotics company that's trying to make bimanual general purpose robots.
Cool.
Yeah.
That's awesome. It's got Spirit AI, is it? Is it launched already?
Yeah, it is launched already. We haven't made a lot of news overseas, but mostly within China.
Okay. That's awesome. That's awesome. Cool. Wow. Okay. Looks like every other researcher we speak to have a either a startup being launched or like in the works.
Yeah.
That's awesome. But cool. But I think for today, like the main focus really is for you to go through FP3.
Yeah.
A really impressive result, by the way. So yeah, maybe we can just dive in, and if you can share screen, you can give
Sure.
a quick overview about what this paper is about.
Okay, let me share my window. Okay, can you see the website? Yeah, so maybe before we diving into the technical details, we can first look at a video of
Mhm.
students eating hot pots, and there is a frontal arm in this scenario, and the frontal arm is able to do several things. I won't be saying it is able to do a lot of things, but I think the nice point about this is that the robot has never seen this scenario ever. It is able to complete all these tasks only using very few demonstrations. So we know from the industry, for example, the physical intelligence, they are also able to do a lot of things, but that is conditioned on collecting a huge number of data. But in this work, we are able to do this without doing a huge amount of data, and that is mostly because we are training a 3D foundational policy. So this is a overview of our called FP3 policy or 3D foundational policy. So it is a 1.3 billion parameter multimodal policy. Actually, that is our work architecture-wise is very similar to for example, Pi 0. But the only difference is that we don't use image inputs. We use 3D point cloud inputs. And that has a huge advantage, both in like in-domain success rates and in the wild success rates. So especially in the wild, as you can see, the baseline models, for example, OpenVLA or DP2 and DP3, they have almost zero success rate, but our method has a pretty high success rate, reaching around 80%. So yeah, so we attribute that to the 3D nature of our policy. Yeah, any questions?
So is that even with fine tuning data? So even with fine tuning data, OpenVLA doesn't do it nearly as well as your policy in the wild.
Yeah, so actually the way we test this is for any new task, we collect a bunch of around 80 demos per task, and then we fine tune, for example, OpenVLA and ours policy in a head-to-head fair setting, and we test it in the wild. So it's its bad performance in the wild is not saying that it's not working in domain. It's saying that it's very hard to generalize to out of domain settings. Yeah.
Yeah, and here, like a task, just to be clear, is something like it's something relatively atomic, like folding a towel or passing a napkin was what was in the video, right? So something like
Right.
that. Yeah.
So yeah. So here the task is relatively simple or atomic. Yeah.
Yeah, could you talk through like how you basically set up? I mean, I guess you train with using a droid data set, and then I believe there's Uni 3D Vid. That's the clock point
Yep.
encoder. So maybe you can talk us through
Sure.
a little bit about the setup.
Yeah, sure.
Mhm.
Very nice points. So there are several details about this FP3 work. So the first thing is that we use a really large scale pre-training. So as you said, we use the Droid datasets as a pre-training corpus. So Droid is a really large scale dataset. It's sort of collected in the wild. Um, because if you really look into the Droid dataset, it's really, really hard. I mean, that's very similar to the home scenario. Then we do some basic pre-processing like crop and furthest point sampling to make it able to fit into the 3D neural network we're using. So after this pre-processing, we have around 86 tasks and total around 60,000 trajectories. So then we use this data to pre-train our FP3 policy. And after the pre-training, it could be able to do some tasks in a zero-shot manner, but not all the tasks. So then we have a few-shot post-training process. So in this case, we did it for 4 tasks. So for each of the tasks, we have around 80 trajectories per task. So that is a pretty small effort combined if you really think of the number of trajectories. So for those post-training tasks, we use LoRa fine-tuning. So that is the data aspect. And for the policy itself, there are several designs we made that we find pretty effective. So the first design is that for the 3D encoder, we're using a pre-trained 3D that is pre-trained on large-scale synthetic data. So, um, so for example, on ShapeNet, so that pre-trained 3D encoder, we find that is pretty important because without that, you couldn't have a very well understanding of the 3D worlds. And although Droid dataset is a relatively large dataset compared to our post-training data, but it's still pretty limited in terms of diversity.
Did you need to do anything to get that to work, or did you do the fine tuning for that for the 3D encoder?
So we use a pre-trained 3D encoder and we fine-tune it. So the pre-trained 3D encoder is called Uni 3D, and we just fine-tune the whole, including the 3D encoder as well as the policy itself, fully end-to-end on this Droid dataset.
And
So
so just to be clear, the droid dataset also have depth information. I mean, sorry,
yeah,
I mean the 3D cloud. Any reason why you choose droid dataset versus some of the other like OKX and whatnot?
yeah. So actually, the main reason is it has 3D information. So
Mm.
we could also use OXE, but maybe not all the parts of OXE, maybe only a subset of OXE where it has the depth information.
That's OpenX embodiment, which we talked about in a couple previous podcasts. Just putting that as
Right.
right.
Yeah. Yeah. OXE is called OpenX embodiment. It's a really large scale data set that um, um, involves many robotic platforms and tasks. So yeah, so the point we are The reason why we are using droid dataset is because it has 3D information, and that is really essential for our method to work, because our methods need to process 3D information, and the 3D information give us the most generalization.
And how about
So
the exact robotic embodiment? Is it the same Franker arms in droid, or is it like they also have different robotic arms?
Right. So a great question. So actually, we're using exactly the same setup as the droid setup. So we are also using a Frankel arm, and we are also using the same gripper. So that is but the camera is different. So because in the droid dataset, the camera is not well calibrated. So you can place the camera anywhere. So the camera is not the same as the droid datasets. But otherwise the arm is the same and the gripper is the same. I think the arm being same is not really important, but the gripper being the same is relatively more important, because the way how you manipulate the object is highly dependent on the form factor of your gripper.
yeah, makes sense. But yeah, so I guess I was wondering what what the difference in roles was between the pre-trained encoder and the droid dataset, but I think that answers it. So the droid dataset is going to tell you roughly how to use the gripper. It's going to help correct for scale, because like a lot of these pre-trained object datasets maybe aren't in metric scale, and so basically it now learns
Right.
how to actually understand scenes from this. But the
Right.
features that it's learned are already useful. Okay.
Right. Yeah, exactly. So yeah, this is kind of the same as many previous foundation model work that employs a pre-training and post-training stages, where pre-training gives you the rough manner of how you can accomplish the task, and post-training gives you more detail about like where to grasp or where to fold, for example. Yeah. So yeah, going back to the main benefits of this methods, I think the main message here is that we should be using 3D representation of in the policy training as much as possible, because that is how our physical world is structured, and how the robot is doing the action in the real world. So this is kind of not super surprising, because this is how nature works. But I want to mention about why previous method don't use 3D inputs, because it seems to be a really straightforward idea, and really an idea that should be really work. I think this is mainly because most of our large language model or large vision language models, pre-trained models, are with 2D inputs. So, for example, the Lava line of work and the Pi Zero line of work, they all follow the large VLM line of work, where the images are 2D, and they are pre-trained in large scale, but only with 2D information. So I think that's why there hasn't been much work in this regime, where we use 3D and large scale, train with 3D. So yeah, so one drawback of our work is also in this regime, where we don't have large scale VLM pre-training. So for example, the Pi Zero work has so the user pre-trained VLM backbone called Polygamma. But in our work, we didn't use any pre-trained VLMs or 3D VLMs, because there doesn't exist any pre-trained 3D VLMs. But we did try to use as much pre-training as possible. For example, the Uni 3D encoder is pre-trained on synthetic datasets. But that could be a future improvements. So if we had a very powerful then our method here could be even more powerful. So that is a future world that I'm looking forward to, and I think that is the trend.
What do you think about work that co-trains on 2D and 3D? Like there's some stuff that has increasingly done this, right? Because you can always project the point clouds down to 2D or something to do understanding, right?
Yeah. Yeah, that's a very good question. I think that might be a even better route than I described because the data is always limited. Yeah, I think probably it is possible to have some sort of encoder that can accept both RGB inputs and RGBD inputs simultaneously. Then we can just pre-train it whatever data we have. If it is only 2D, yeah, I think that should work really well.
Yeah. Maybe if you can, I know you have some video about the specific task. Just to
Sure.
illustrate what kind of tasks are we talking about. So
Okay. Sure. Yeah, maybe let's look at some videos. Okay, let's see. So for example, this is the old tower test that we tested in our doorway. So this is playback in this original speed.
so this is in domain, right?
Yeah, so this is in domain. And let me see. So this is general. So this is some generalization, but this is in some other task. So here the task is pick the trash and put it in the trash bin, and this is the in-domain scenario where we collect the data. So we have quite a few ablations. For example, different background. It generalized pretty well because the 3D structure is very similar. And for example, it can also generalize unseen distractor. So we have several toys that is placed on table, and it can also generalize to that scenario. And unseen objects, for example, the trash bin is different. You can also generalize to that.
Yeah, it's always
And
impressive how well these 3D models can generalize compared to, I think, the purely 2D
yeah,
ones. Very cool.
and also unseen camera views.
So for this particular task during in domain, like you collected, you mentioned was it 80 demonstration for this
Right.
particular task? Can you
Right.
describe like what is the variation of this 80? Like is it exactly in the original environment and just do it 80 times?
Yeah, it is in this environment, and we do it in 80 times, but the position of the trash and bin is different every time.
I see.
Yeah, it's not like we have exactly the same position as well. So only the object is the same, environment is the same, but the position of those objects are different.
Got it.
And
Yeah,
also,
yeah, go ahead.
one other question that I meant to ask earlier. So, what is an action to you? How do you define it?
Yeah, so the action here is the end effector's delta position and also the delta gripper action. So that is action space. Yeah, I was about to say the in domain here is so this is a kind of like a generalization ablation experiments that aims to study the generalization, how generalized the method will be. So we artificially create a setting called in domain where we only modify the position of those two things and all other things being the same. So this is specially designed in this task so that we can, for example, easily verify, for example, the changing of the lighting condition, how generalized our method is. But in the general case, for example, the Tao folding task, we didn't define the in-domain to be only as restricted as this in-domain setting, because always the same, the more diverse the data you collect, the better it will generalize. So for the other tasks, we didn't restrict our in-domain setting to be so not diverse.
So this is done basically 0 shot after you've done the fine tuning of the AD demo of the same task.
Yes, right.
How about the failure recovery rate? Let's say if it's
Fail.
like qualitatively speaking, could you describe like is it pretty robust to that as well?
We actually the methodology wise, it is able to do the failure recovery, but we didn't. But you have to collect demos to enforce that. The base policy is able to do some level of failure recovery, but it's not able to consistently do the failure recovery. But for example, if for example the gripper couldn't pick up the trash,
Mhm.
it might retry with some probability that it might retry to pick up the trash, but might not might be given up at some point. But if you collect more data around the failure recovery, it will do it much better. So it's just a matter of how you do the post training. If you do the post training that's with a lot of emphasis on the failure recovery, it will do that.
Yeah. There's this table in your paper. I think it's the one that actually breaks down the success rate of the different tasks. Could you go to that table? Because I find that table pretty impressive. If
Okay.
you, yeah,
I
the
mean,
absolute numbers. Yeah, if you can talk us through a little bit like what you observe. Yeah, yeah, that table just now.
oh, is this
Yeah, this one.
okay?
So,
Okay.
so could you talk us through like what does it mean when it say 90 like for full Tahoe? Is it
Okay. Um, yeah. So this is the success rate evaluation of our methods. So here we have 4 tasks: for towel, clean table, stand up cup, and pour water. So yeah, maybe let me show you some more videos. So this is a full towel. Oh yeah, this is actually a evaluation video that we evaluate in the wild. We didn't actually collect data in this doorway. So this is evaluation scenario. And this is full towel, where we just want to fold the towel in various scenarios. So this is the first floor of our building, and our office is at the 19th floor. So this is a not successful case. It tried to fold it, but didn't actually pick up the towel. So let me quickly go through the other task to show you a basic idea of what it looked like. So this is a stand-up cup. So a cup is flipped it on the surface, and we try to flip it up. Yeah, somehow I think those videos might having some issues because they might be cut off early, because I think it's supposed to be a success video. Okay, this is a failure video. Okay, failure chance and succeed. Okay, um, yeah. So this is a stand-up cup task, and this is a put things in trash task.
Guy, can I ask like so during the demonstration phase, right, when you guys are doing the tally op, do you find the human tally op to be roughly doing it at the same speed as eventually when you deploy it and let the model do it? So it's roughly the same speed. So even a human
Yeah.
tally operator will take roughly the speed to do this task.
Right. Yes. Yeah. So because the human teleoperator is using a VR control,
Mhm.
so is also doing it relatively slowly. So that's why the robot is also doing it pretty slowly. Got
But
it.
that's not a limitation of the method. Like you could go a lot faster with different data,
Yeah.
I think. Yeah.
Yeah. Yeah. So there are a lot of system engineering work that we didn't do. So for example, the teleop, the speed of the teleoperation. So one of our previous work called the data scaling law. Yeah, not sure whether you have read it, but in that work we used UMI data collection device by Professor Shuran Song at Stanford University. So that is not a teleoperation device. It's a handheld gripper that human hands can hold it and do the work without any robot in the well. So that data collection device is much faster than teleoperation. And we find that the policy train using that data collection device also has a quicker movements compared to teleoperation data. So another thing we haven't done engineering here is you'll see the robot is moving a little bit and stop, and then moving a little bit and stop.
Mm-hmm.
So that is because during inference time, we are not doing the inference and robot execution in parallel. So yeah, we are just doing in a pretty naive way that we do the inference and execute that, and then wait for the next inference to be done, and then roll out that inference. So yeah, that is also something you could engineeringly optimize it to make it look more smooth.
Got it. Cool. Yeah, I was wondering because like you say, it sometimes start stop start stop. So I was wondering whether it's thinking. So, but it sounds like it's thinking.
It
Yeah.
is actually doing the policy inference in that second or half a second. Yeah. So the last one is pouring water. Yeah, we didn't actually pour it, but we asked it to pour it and put it onto some target cup placement place. So those are the 4 tasks we are trying to do. And so we test a bunch of methods. Diffusion policy is a method that use 2D inputs and no pre-training. And DP3 is a method by my colleague at Tsinghua University, Professor Huazhe Xu. So their method is also using 3D information, but DP3 doesn't have any pre-training. So we can think of it as a version of our methods but scaled down, and no dry pre-training at all, and no pre-training encoder at all. So this can give you an idea of how the pre-training helps and how our design architecture helps. And OpenVLA is a method that has 2D inputs. And so basically it's very similar to DP, but has a lot of pre-training baked into it.
What's FP3 Scratch? What's the difference between yours and FP3 Scratch?
Yeah, so FP3 is our full method, but FP3 Scratch is we throw away the dry pre-training. So
just the dry pre-training. So the encoder is the same.
Yeah.
Yeah.
Encoder is all the same.
Still pre-trained, I guess. Is what I mean. Yeah.
Oh, the Uni3D encoder is also pre-trained, but we just don't pre-train the policy with the dry data set. Yeah, as you can see, if you look at the average, the in-domain our method is drastically hugely better than all the other methods. So I would say this is because we have the pre-training, and also 3D is able to transfer much better. And not, yeah, go ahead, Chris.
Oh yeah, so these are huge differences, I guess. If you're listening to this, then we have the averages are 35, 22, and 7% success rate for the baselines versus 95% for FP3s. So that's incredible. Yeah, that's a huge difference. So you think this is basically just because of the 3D as well as, or is there more to it? Or is that just like really the lesson is everybody listening should be adding in more 3D information, I guess?
Yeah, I think so. I think everybody listening should be adding more 3D into your policy. Because that is what we found has made a huge difference. And yeah, for people who are only listening to this, there is also another testing called in the wild testing results. So yeah, just now we were talking about in-domain settings. So our method is like 95% versus all the other method topping around 36%. However, for the in the wild setting is having an even larger difference, where our methods is having an 82% of success rate, while all the other methods basically fails, topping around 4% of success rate in the wild.
So one other question though. So we've all seen videos of diffusion policy. Like it's one of the more common ones in the robot and all this. So like it can get better than 35% success rate. So like is the reason there because like even your in domain has a wider distribution than usual, or can you explain this a little bit more?
Yeah. So yeah, a lot of people might be confused about why this paper only has 35 while some other paper has 90 or even higher. So this is because the distribution you are testing is will highly impact the success rate. For example, for any task, for example, this water pouring task, if the randomized location of the object is, for example, 100% larger, then the success rates might be dropping pretty drastically. For example, might be dropping from 90% to like 60%, for example. So the randomization range is drastically different, and also the number of demos we collected is only 80 demos. So that is also much smaller than many of the previous work, where they might be starting from at least 200 demos and might be going to a few thousands and even tens of thousand demos to finish a single task. So that is why you see the DP only have around 36% for in-domain, in-domain performance.
Makes sense.
So just to be clear, for the actual test, for each of these tasks, you try 5 times, something like that.
Um, I think not 5 times. So with each object, we try 5 times. Yeah. So
Looks like 20
tested,
overall from the numbers. Is that right?
yeah, I think if I remember correctly, it's around 20 total trials for each of the numbers here.
I see. Got it. So for example, if it's DP did 20%, then out of 20, it probably did like 4 success rate, something like that.
Right.
Whereas the if it's 90, then it would done 16.
So 5 trials each, 4 different objects, I guess. For like, so pouring water, you would pour water with
Yeah.
four bottles.
Yeah.
Got it.
Yeah.
Okay. Cool. And yeah, that's really impressive. Like 95%. So what do you think happened to the other 5%, or even in the wild, like those let's say nearly 20% failure? Qualitatively speaking, could you talk about like how does a model fail, and how do you think it can be improved further?
Yeah. So I think the model fails. So I think this is a sort of the failure mode. I won't say mathematically or algorithmically, it is fundamentally different from all the other methods. It's just out of distribution that at this particular location, you might get some sensor noise. For example, you couldn't see some parts of the object that is behind it, and you just didn't cover enough diversity in your training data such that your policy couldn't do it really well. So, I mean, it's just the usual out of distribution thing that is happening in the remaining 5%. So, for example, some of the video I just played show parts of the failure mode. For example, sometimes they couldn't grasp it really accurate. This might be a success video, I think. Or sometimes they couldn't pour it really accurately. Yeah, this is a success one.
So you mentioned out of distribution. So do you think you get more bang for the What about, rather like, do you think you just need a bigger Droid data set for pre-training, or you just need to do
Yeah,
more demo for fine-tuning? Like, which one do you think you go for?
I'll go for more demo for the fine tuning. Yeah, more demo. But I mean, improving both sides will definitely helps. But if you really want your policy to be able to do one task, then just do more fine tuning. That is much easier. But if you want your policy to be overall more robust and perform better for many different things, then do the pre-training, scale up the pre-training. Yeah,
Well,
I think that's
presumably also like as you collect more demos for a single task, you can feed it back into pre-training. Did you try throwing
yeah.
in any of the other ones into your pre-training, or no time for that when doing this?
Yeah, we didn't have time to do that.
Yeah.
Yeah, but the thing I want to mention is that um is that it is expected any methods will have some level of failure rates.
Mm.
If you make the setting really hard, so it will always fail. I think the point is so you can imagine if you plot on a 2D to the plot where the x-axis is how many data you collect, and y-axis is the success rate in a, for example, extremely hard testing scenario, and all the methods will have a success rate increase when you collect more data, but different methods will have different curves because of the difference of the method itself. So I think the point here is that the FP3 or any 3D based VLA policies will have a steeper curve that increase much faster in the beginning so that you can reach your desired, for example, 99.9% of success rates with much less data than the pure 2D policies.
How do you collect the point cloud, like concretely? What device are you using? Is it just
We use Intel RealSense,
okay?
just as everybody did. Okay.
Well, yeah. So instruction following performance. So anything.
Yeah.
These are the. So you can train a single multitask model.
Right. So this is saying you can train a single multitask model and you can input an instruction to it and you can follow the specified task. However, yeah, the limitation here is we only do 4 task fine tuning, so it's very similar to one hot encoding.
Mm.
But yeah, I mean, if you can collect more data, this will also work.
Yeah, and presumably, if you actually use an VLA instead of, I think, the clip that you're using right now, you can be very qualitative in the natural language instructions, right? So instead of fold towel, you could say fold a piece of cloth, and it will still be able
Yeah,
to figure out.
right.
Whereas right now, because you didn't do that, okay.
Yeah, exactly.
With like proper support from training data.
Yeah.
Yeah, makes sense. Cool.
Yeah.
Great. Any last takeaways? Anything like, so I guess we already mentioned this, but the big one is the 3D, or what? Anything you think
Yeah.
that people should take away from your paper?
Let me see. I think another takeaway I didn't really mention is the size of your neural network. So our method here is a 1.3 billion parameter neural network, and we do find that smaller neural network work much worse than the bigger ones, especially with the pre-training. With the droid pre-training phase, you won't find this scenario. You won't find this case if you're using a small data set to train your model along without any pre-training. Our experience is that with pre-training, larger model do perform much better than smaller ones. Yeah. Yeah, let me see any other takeaways I have.
It's a 1.3 billion, right? If I'm not wrong, the parameters.
Yeah, 1.3
Yeah.
billion.
And it's was it like 800 or something like that? And then you train for a couple of days. So it's still not like crazy compute, I guess.
It's not
Yeah.
a crazy compute. We just train it with 8 GPUs.
Yeah.
For a couple of days, not really long.
And at inference, you just run it on a single GPU, another 800, basically.
During inference, we run it on a consumer grade GPU card. I think it is 3090
Okay.
GPU. Yeah.
Okay. Got it. Yeah. Yeah. This is very doable. I mean, I guess the main compute cost is only during the pre-training phase. Once it's done, then at inference,
Yeah.
it's actually very doable.
Yeah. I mean, you have a similar setup to ours. I think the similar setup is only the gripper. You don't necessarily have the arm itself to be similar to our setup, because as long as you have an arm that can reach that place, the arm can do the IK by itself. So I think it's pretty much arm, also arm agnostic. So if you have, if you want to replicate our work, then just buy the same gripper and install it on whatever the arm you have, and fine tune it. It should work.
Which gripper was that? Is it the Robotic gripper, or is it?
Yeah,
Yeah,
it is
Robotic
a
two
robotic.
finger.
Yeah.
Yeah. So just to wrap things up, right? So usually I like to ask the last one two questions, the same last one two questions, which is, Gaoyang, if you let's say have another 1 or 2 more months, like to left like more to work on this paper, like what would you have squeezed in to this paper?
Let me see. I think if I have 2 more months, I'll make the engineering look better. I will make the robot move smoother,
Mm.
make the data collection move faster, so that our robots could have faster speed, so it can look better. So that's the thing.
I think you are the first person who has answered that with, "I would do better engineering," instead of, "I need more
Yeah.
experiments."
Oh, really?
Yeah. Well, I mean, it's the fifth one or so.
Okay. Okay. I think experiments wise, it will be
I'm not
similar.
saying it's a bad thing. I'm not saying it's a bad
Yeah,
thing.
yeah.
You can say I've done all the experiments I need to. It's okay.
Yeah, I think
Yeah.
we have done all the experiments. Although it's only 4 tests, but we have tested pretty well-rounded testing. But I think, Chris, the idea you mentioned is great. I think I might be restarting a new project doing that. So if you're interested, we can collaborate on that.
Awesome.
I mean, the 2D and 3D joint training. I think that is very interesting.
It's a very cool kind of direction, I think. There's some people who've already like started looking into it, but it's one that I think is really exciting.
Okay.
No, so much. Yeah.
Okay.
It's very exciting. Yeah.
You said someone is already working on that?
I know maybe one paper I can think of that's really doing this. So I think it's very up in the air. I don't think there's a lot of,
Okay.
I'm very curious as to whether or not it can really work for like this kind of, no one who I've ever seen do it for like robotics tasks either. So it'd be,
Okay. That is,
yeah.
okay, that is doable. I mean, for robotics and non-robotic tasks is quite different. So yeah.
Well, maybe a final question, at least for me, is there any paper that you come across recently that like completely blew your mind? You want to give a shout out?
Yeah, I do think there are a few paper not blowing my mind, but I think it's quite worth to read. I think the NVIDIA Groot paper, or they call it GR00T.
Yeah, good.
The NVIDIA Groot paper it's very interesting to read. Although there are not so many ablation experiments, but I think the insights or the way they develop the foundation robot models is very interesting to look at. Let me see. And also, there's a recent paper from Shuran's group called Unified
Video.
Unified
Yeah.
Video Action
Yep.
Models, something like that. And that
Using
is,
one model to predict
yeah,
like video generation thing.
Yeah, that is also very interesting to look at. That is something I have been thinking about, but I didn't really do it. And it's really good to see someone tried it and see how well it works.
Mm.
So that's, let me see. Yeah, that's the two recent papers that I find interesting to look at. Yeah.
Very cool.
Yeah, that's it for me. Chris, do you have anything?
I think that's
Okay,
great.
cool.
Thanks for coming on. This is a lot of fun. Very cool work.
Yeah.
Yeah.
Yeah, it's really nice to have you have me here, and really nice chat with you. And yeah, also really nice to meet you again online, Michael.
Yeah, definitely.
Yeah.
And congrats on your new startup. Yeah.
Yeah, thank you.
All right, Chris, what do you think? What do you think of the paper?
Yeah. So I think I'm always a big fan of 3D stuff, 3D policy learning, actually. I find that I think that if you care a lot about generalization and robustness and reliability and all these other things that we want robots to be able to do, I'm always interested in hearing the newest developments. So like I think this is a cool work because it takes like kind of the recipe that's worked so well for like vision like VLAs these, and it has kind of applied it to as much as is possible to a 3D kind of policy learning context. Like, and they show some, and he shows some cool results where we have the robot generalizing and handling distractors and all the kinds of things that we would expect to see with a 3D model with far less data than you get to see with like than you see for like OpenVLA or one of these other kind of models. So yeah.
So do the absolute like success rate like surprise you? Or do you think it's still hard to tell? Because
I don't know. I mean, I think, I guess no. Yes, no. I mean, I think it's impressive for sure. So the absolute success rate that you see in this paper is like in domain 95 to 95%. So 19 out of 20 trials successful. That's very good, right? That's and then there's with the
in the wild,
and then in the wild one assembly it's like 85%, so like 17 out of 20 trials successful. So these are very good numbers, I think. Very strong results, beat the baselines by a lot, and the baselines are ones that make sense. Like there, I think the reservation and the big problem with a lot of robotics papers is that those are all their environment, right? So like,
how in the wild
I think
truly
it's quite
is
good.
in the wild.
Yeah, it's quite very good.
Fair
I think
enough.
it's like. Like there are so many little things that affect performance, right? But that being said, I think that this is like, I do think it's very strong. It's really cool work, really cool direction. I really like the 3D policy learning angle, and I think this is kind of the right way to go about making these systems work really well, because you can see like intuitively, like it's just the kind of thing that it makes sense, right? Like you should be able to like. A lot of the time, by adding in this depth sensor, you're making the problem so much easier to learn, because like really like a lot of what you're doing is just identifying a point in space and having the arm move towards it, and like that just falls out of the 3D representation in a way that it doesn't from a 2D one, right? And so
yeah, I guess I mean for me I think that the thing that I really wanted him to come on the pod was when I saw the success rate, I was like, okay, I rarely see this like 90 something percent, like, you know, in the wild 80 something percent. I was like, okay, this is something different. Yeah, and then also I guess I'm a big believer in just like keeping the hardware very, very simple, right? And you know, that way you can keep the cost down. And you know, depth sensor has the cost have gone down a lot, but it's still nowhere near what a cheap camera can do, right? I mean, a cheap camera is like, you know, a few dollars you can get a decent camera these days.
Oh yeah, no. Whereas like a cheap depth sensor that's good, it's like a couple $100, so it's like close to the cost of your robot probably, or like like if you're getting a really cheap robot,
yeah. So I guess it really depends on the like how cheap you want the robot to be. I mean, if it's the robot ends up being, because all the battery and the actuators ends up being a $10,000 thing, then you know I think the depth sensor is not like percentage wise, it's trivial. Yeah. So I think he makes a very strong case, you know, that if you really want decent performance, from the get-go, you probably should just put a depth sensor in there and then
the
have
other
a
thing
3D
is,
model.
yeah, how much are you spending on compute? Because like if you need it, so this was a 1.3 billion parameter model, right? So that means that you can fit it on a relatively, they used a 3090, but like you could fit
That's
it on a much
inference.
smaller GPU than that, right?
Mhm.
Like because you probably only right now. That being, but if you were trying to do this, and it's just a VIT fine tune too, like the 3D, the 3D is very nicely done. So you could do a nice quantized version of it. Probably you could fit it into a relatively small, as opposed to needing like a really, like if you're spending thousands of dollars on GPU compute and running to run like a 7 billion parameter model, maybe you're not actually saving money by using an off the shelf camera, cheaper camera, right?
I see what you're saying. That's a very good point. I see what you're saying, because the model being the policy model being so performant, you end up being actually having a smaller inference cost, and therefore you just need a smaller GPU.
I mean, the compute is
on the
happening
robot.
somewhere, right? You're having that 3D thing, the reasoning is happening somewhere. And is it happening if it's happening in the GPU versus in the camera? I don't know which one's better.
Yeah.
That really depends on so many other factors, right? That's
Yeah.
yeah.
Yeah, but I think what you asked him, clearly was something he was thinking about as well, like basically 2D and 3D.
Yeah.
Not just the point cloud, which is what he did here.
Yeah,
Cool.
it's something that it's on my mind because I don't think anyone's really done a great job with this, like lifting 2D to 3D and making sure, like, can you train these things? Like, people have done actually very cool work in it, but I don't think I've seen any like robot policy learning stuff that does it. And so like I'm really curious as to whether or not like that's the direction people end up going in, because like I personally am a big believer in 3D. But the biggest problem right now is that we just don't have the data for it, right? So he was using Droid, which we talked about last time or 2 episodes ago or whatever, being actually a pretty bad data set in a lot of ways. Like, and he's able to get quite a lot of weight out of it. But like, and I don't want to insult the authors of Droid or anything, but I think that was the value function one, the Gemini value function, right?
Yeah.
That they're talking about the issues with this data set. So like, you're very limited by data with 3D, but it really does go farther. So like it's something really, and it made a huge difference for him to use this data set, which was actually quite problematic for Jason Ma when he gave his when he was on the podcast, right?
Yeah,
right.
That's true. Interesting. It's also interesting to me that he said that he would spend more effort, not on the pre-training, like more data on, but just squeeze a bit more demo, for fine tuning. Because he only did 80 for each task, so he can probably easily do a lot more. Yeah. Cool, fascinating stuff. Okay, cool. Yeah, maybe hopefully when there's a paper that comes up that do exactly what you described, like 2D and 3D, we should definitely get the author up onto the pod.
Yeah.
Cool. Yeah, then we'll do it next week again.
All right.
All right.